destroy the town, and in the night, LNG chemical plant explosion because operator excavated without shutdown of this plant. Big and huge explosion of plant. And what's worse, the tsunami encroaches into Fukushima nuclear plants. There are 6 and 4 nuclear plants. Nothing to do. They lost the electricity outside, especially electricity for water supply to nuclear plants. Then next day, explosion. This is not just explosion. This is a hydrogen explosion. And the core of a nuclear reactor melted down already. And now we are making this commissioning. Probably it takes 100 years to take out the debris and to finish decommissioning 6 nuclear plants. This is a shutdown of nuclear plants and the damage of energy infrastructure. 11 sites of nuclear plants fell into shutdown, and LNG gasification plant were damaged. This is a destruction of transmission lines and buildings by earthquake and tsunami. And same time, gas plants damaged so much. Before tsunami, we have 54 nuclear plants. This is number 3, United States, France, and Japan. And before tsunami, 10 units are in maintenance, then already stopped. Then no damage at all. But by tsunami, these 11 sites get damaged. And yellow part, like this, is under construction or under planning for future nuclear plant. All the plants planned and frozen or suspended. And after that, all the nuclear plants in maintenance one by one. And 2 years ago, no plant in operation out of 54. Then Japan is suffering from a lack of electricity, at the same time, high cost electricity. And now recovered one by one, and now only 3 nuclear plants out of 54 are in operation. Very miserable situation. Before tsunami, Japan has very good generation mix. In 2010, nuclear plant is almost 30%, LNG 30%, and coal 25%, very good generation mix. But tsunami 2011, all the nuclear plants has gone. And after that, nuclear plant is only 1%. Then we have to increase fossil energies, LNG 40, and oil more than 13, and coal 30. Then 87% of electricity is generated by fossil energy. And after that, 9 years passed. And OCTO is neutral organization of Japanese government, estimated at the year of 2016 for 2020, this year, generation mix is still the same, just as in tsunami. Nuclear plant still 1%, LNG 34, coal 30. And we increase a little bit sustainable energy, but only 19%, including hydro plant. Then in Japan, still it is necessary to reduce the consumption of fossil energy and to increase generation by sustainable energy. And also we have damage by earthquake, August 2018. The magnitude 6.7 earthquake struck and knocked down power system. And 5.4 million people was in blackout. This is the earthquake in Hokkaido. Hokkaido is a northern island of Japan. All area was in blackout. This is the first time of Japanese history and the largest blackout in Japan. It took in some area, especially remote area, it took over 1 month and big damage for residential people. And not only blackout get damage to industry and agriculture and fishery and public works and so on. In 2019 September, the biggest typhoon, this is a new record, the biggest in typhoon and hurricane in the United States, went through Chiba Prefecture. This is a Tokyo area. This is Chiba Prefecture. Went through Chiba Prefecture. This is a transmission tower collapse. And the 2,000 electric pole collapse. This is Tokyo area in the light, but this is all in black. But only one good news, in Chiba Prefecture, all in blackout, but just one area, electricity are available. This is this one. This is called Chiba or Mutsuzawa Wellness Town. This implemented sustainable and resilient energy system by using cogeneration, PV solar system, and EMS system, and PV water heating system. And after 5 hours of blackout, this area recovered, and electricity, communication, and hot water and shower were available. This area has 30 houses and 160 parking area. And this is the restaurant and the shops and the hot spring. This is the flower and vegetable and fruit shop. I'm proud this wellness town was designed of our group. And also we designed the cogeneration EMS system. Then now in Japan, sustainable and resilient energy system is in boom. I'm very proud of this. Now, after tsunami, we made a paradigm shift toward best energy mix from nuclear central generation mix. This is a conventional power system with long distance transmission line, large scale plants. But large scale plant as attacked by tsunami 2011, then we have to change our mind. After 2011, we made energy saving. Usually 15% to 20% saving has been done. And the local government had local generation, such as microgrid and so on. This means the best energy mix based on distributed generation and distributed network. As a technology, other than nuclear plant, energy is clean and cheap and stable. Energy thermal plant constructed, and gas combined cycle, the gas engine, and coal, and hydrogen use fuel cell. This is very popular technology for energy supply. And somebody likes sustainable energy, but it means fluctuation of sustainable energy. Then we always install battery energy storage. But somebody said, very expensive one. Then the Japanese government has pushed forward to use battery in the electric vehicles. This is a future energy technology. And sustainable energy has advantage, but has a disadvantage. For example, this is a fluctuation of PV generation. This is the example of summer. In a fine day, 70% output. A cloudy day, only 40%. Rainy day is 15%. And PV generation causes this voltage problem in the feeder of the system. PV panel generate electricity leads to power from this side to this side. This power is called reverse power. Power utility never thought about this reverse power. They have no countermeasure for this reverse power. At the same time, voltage at the feeder end increase, and sometimes excess the upper limit of voltage limit. In that case, we have shut down these panels and these panels. Or we have to install some voltage controller. But who pay for voltage controller? And also, wind fluctuation cause frequency problem. This voltage problem and frequency problem used to be mitigated by power utility. But nowadays, our customer should contribute to mitigate these problems. Installing smart meters and batteries, electric vehicles, and also visualization of this situation. But this is very complicated. This is called smart house and very complicated. Then usually we have to install this one, home energy management system, EMS, to keep the supply and demand in balance. And conventionally, we constructed almost 10 years or 15 years ago, a microgrid. This is called conventional microgrid for local use of local energy resources. Microgrid has this kind of loop structure, and customer receives electricity from this loop, and the supplier and supply electricity to the loop, this one or this one. In order to keep the balance, supply, and demand, we install energy management system by using IoT and ICT and so on. This is software backup of microgrid. That's not sufficient. We also install this one, battery energy storage system. This is hardware backup. Two backups, but still not sufficient, because some fault of this equipment, we loss of electricity. Then usually microgrid connect to the grid for emergency backup. Small system and 3 backups, it's very costly. Then the conventional microgrid instead is very expensive compared with conventional power system. Then these 10 years, this microgrid is not so constructed, especially in Japan. And in 2009, President Obama proposed smart grid. Without changing power grid, they the grid smart. Now in Japan, we are installing smart meters, almost 50%. Then it takes 5 years more. And after 5 years, smart grid will be completed. But smart grid development is held all over the world. For example, Korea in Jeju Island, and Singapore in Jurong Island. And in Japan, we have big government project, Yokohama, Toyota, and Kyushu and Kyoto. And China is very aggressive for constructing eco-town. For example, Tianjin, Tofan, Dalian, Hainan, and so on. In the United States, some project, Los Angeles and Hawaii, Boulder, Miami, Los Alamos, Albuquerque. Most of projects are undertaken by Japanese company. And Europe, very famous one, the Desertec project. This is a very famous smart grid development in China. Singapore government and Chinese government make a shake hand and cooperate to construct this kind of Tianjin eco-town, including PV generation. 20% of electricity will be generated by PV generation, and regional air conditioning, electricity saving, and waste and water treatment of whole the town. And 260 people is expected to live in this area. But only 5,000 people live here because this new town has no job. No job. It is not attractive for young people. Project itself is very successful, but people is not interested in this town. And this is a Korean Jeju Island project, national project. Many kinds of energy-related facilities, wind offshore, wind onshore, and energy storage, smart house, smart school, smart substation, and so on, and the PR center, and like this. Now, this is a very good showcase of smart island, smart grid in Korea. Now, this is a future power delivery network. This is my estimation. Our customer always requires stable power, reasonable price, and clean electricity. And then naturally, electric company must construct large-scale power system like this. This is called Edison model or Westing model. But this model is not anymore because it's very difficult to construct remote large-scale generation and a long transmission line. Construction of largest transmission line is anymore in Japan and Korea and also Asian country and European country, especially Germany. Of course, it is possible to construct this kind of large-scale system in China and Arabic country and Africa and Australia. And also, we have a vulnerability, this kind of large-scale system. Then we have to change our mind for future social infrastructure. Now, President Obama present smart grid, but it's very expensive. We have to invest to smart meters and the communication system. And after getting information from the grid, customer reduce their consumption. This is not good for power utility from the viewpoint of cost benefit. And conventional microgrid, this is too much dependency on the grid. It's not autonomous. Then what is the future social infrastructure. That is searching for comfortability, smart and eco-life. It is smart community, not only electricity, heat, waste, lifestyle, transportation makes smart. The second one is a search for resiliency, usually driven by local government. It is expandable microgrid. These are not conventional microgrid. Microgrid connect each other and extend step by step. And one more future grid is a resource accommodation, a transfer crossing the border. It is sometimes called supergrid or a global energy interconnection proposed by State Grid in China. This is a future trend, smart community, expandable microgrid, and supergrid. The first one is autonomous and comfortable life of smart community. Smart community is not only power system, include heat supply and lifestyle change and also transport. All the sector become smart by a smart community. This is one example of smart community pilot project in Japan, Yokohama area. Yokohama area is divided in some district. This is a microgrid. Small area is called microgrid. And this area equipped 7 mega PV, 4,000 smart houses, 2,000 electric vehicles by Nissan. This project was done by Toshiba, Nissan Automobile, Tokyo Gas, Tokyo Electric Company, and Yokohama City, and Maiden, and Accenture. And the total budget is $1 billion for 5 years. And already this project was finished, but the target to reduce 30% CO2 by 2025 was attained. Means this project was quite successful. Not only Japan, Japan is developing smart community all over the world. Lyon, France, and Manchester, and Miami, and Malaga, Spain, the Java Island, Indonesia, the Los Alamos, and New Mexico in the United States. This is a site of Los Alamos, a PV, lead acid battery, and a micro EMS. Micro EMS is EMS for microgrid, proposed by Toshiba and Shimizu Construction Company. This is Albuquerque. Targeted building is Del Mesa del Solar, 500 kilowatt building. And this is the implementation facilities and the gas engine and the energy storage and the PV. This is a micro EMS. And this is a micro EMS functionality. The range of another project is around here, including PV and buildings and batteries. They monitor this situation. At the same time, they are monitoring the connection and try to make this power flow constant. This is the actual measurement of operation of this microgrid or smart community. This is load demand, change of load demand. To meet load demand, PV output, supply electricity, NAS battery, and lead acid supply. The target of this system is to make this power flow constant. This is a power flow in this microgrid. This is very constant in any load change. Means this EMS and microgrid and smart community were very successful. The next one is resilient and sustainable microgrid, especially driven by local government. After tsunami, we make energy saving and the peak cut, and the combination of saving and peak cut like this. And also smart house had a good reputation. This is proposed by Toyota House in Toyota City. They equipped the PV panel on the roof and the domestic battery and fuel cell and gas cogeneration, small gas cogeneration, and electric vehicles, all very expensive. Then this house is very expensive, but very good resiliency. In case of blackout outside, this house can survive 2 or 3 days without any supply from the outside. This is sustainable and also resilient house. This idea is extended to house to area. We make the group of houses. Each house is not always necessary to equip these energy-related facilities. Some house has panel, some house has electric vehicles, and they transfer the electricity in this group. This is extended to the area. It is called microgrid. Excess energy is transferred from this area to this area. Or sometime in the midnight, office district supply electricity to the house, like this. This is a typical configuration, resilient microgrid for power supply. They have sustainable energy and a conventional generation system and the demand. Now, this is a connection to electric grid. This system is called back-to-back connection. This side AC by using a main inverter DC. DC can connect a battery, and also interconnection inverter convert electricity to AC. And we can connect or disconnect this microgrid to utility. And this inverter has a function to control voltage and frequency in this microgrid. And this one have a power flow control at constant point, constant value, or we can disconnect from the grid. This is a minimum unit of microgrid. And this microgrid can interconnection and expansion, can expand. Microgrid can connect to microgrid 2 because they have EMS system, voltage control, frequency control, power flow control, and connect to A and B and C, and also connect to the power system. Then this is called expandable microgrid. We propose firstly to developing countries. For example, there is a customers, we construct this one, and the next village, we construct this one, and after that, we construct transmission line, and the third one, we connect this one. Because this customer want to have electricity, not transmission line. Then this system supply electricity first, and transmission comes next. Then good for developing area and the regions, and islands and remote areas, and the metropolitan area. It's good for emergency supply in case of blackout in the system. This is a demonstration. I get the fund for $5 million from the government. This system is a $1 million system, microgrid 1, microgrid 2, connected each other or disconnected. This is a measurement. This is a single autonomous operation. And voltage and frequency has been kept in prescribed value, quite successful. And the two microgrids connected each other. First, voltage and frequency is different in each microgrid, but finally converged into one. This is a SOC of battery, frequency, and voltage converged into one. Means two microgrids merged into one, united into one. And this system is installed in Yamagata Prefecture from 14 to 18, and operation was quite successful. The microgrid 1 is City Hall, and microgrid 2 is four houses, social houses. And the operation was quite good. And this the time. I have not so much time, but I would like to introduce microgrid designer. Microgrid design is like this: structure and the component and design of microgrid like this. First, we have to grasp the sustainable energy generation, PV and biomass wind in this area. And also we have to grasp the existing generation facilities, micro, hydro, and something pumped up, and the diesel and gas generators. And the most important thing is to get load profile: shop, hotel, office, residence. The shop is, load is like this, only daytime. Office is daytime. Hotel is from the evening. Residential area is, peak is in the night. We aggregate all load profile, and we supply by using these generation facilities. And if necessary, we install battery. And this is a connection to the grid. And in order to operate or control this system, we need to construct energy management system. Energy management flow is like this: input, demand, and generation. And we select the generation resources, including sustainable energy, and also analyze power flow, frequency, voltage, and so on. And if necessary, we install and decide the capacity of battery. And finally, simulation of the system over 24 hours, or 1 week, or a month. And for analyzing microgrids, first one, the economic load dispatching. Generation facilities. And first we calculate snapshot, and 24 hours multi-stage economic dispatching calculated. And this result inputted to power flow. And we conducted single stage power flow, and finally 24 hours or 1 week. This is a typical microgrid used in our system. This is one example, island in Caribbean island, Saint Kitts Island. One thermal generators, PV generation, and small hydro, and a gas engine, and many roads. Now this is the input, actual input, connection of node, and electrical parameters, and demand, and so on. This is after calculation of over 24 hours transition of node voltage and power flow. At the PV node, in the daytime, voltage increase because large amount PV from this node. This is the generation mix over 24 hours. Red one is PV, only daytime. This is summer. This is diesel, cheaper diesel, and diesel second. And this one is constant hydropower. This is the generation mix over 24 hours after calculating multi-stage economic load dispatching. And also in real-time operation, we need to design the EMS system. EMS system control and manage the microgrid by using monitoring, visualization, remote control, and demand response, and emergency state control, and also monitoring resilience. It's called home security. This EMS consists of three functions: load forecasting, operation planning, and real-time control. Because of time, I'm skip this one. And this is application to 1 week analysis. This weekend is the load is very low. And this is the after analysis generation mix. The cheaper one comes first. The gradually expensive generator supply electricity. The red one is battery. This is charge of battery. This is discharge of battery. This is come by microgrid designer developed by our group. This is the last part of my presentation. Today we mentioned about the resilient expandable microgrid. Relatively safe area, highland, we construct microgrid. Now surrounding this one, we install storage and solar, mega solar and wind, and construct city office, hospital, retirement house, and an emergency center. And in case of a blackout and electric utility, people come into this area. This area still electricity, communication, and water supply are available. Means this area gives the people resiliency for this community. And we are going to construct this microgrid one by one. This is a mistake, microgrid one by one. And the first step is energy management, electricity facility in this microgrid. After construction, there are several microgrid, power exchange between microgrid, then the microgrid connect, extend, expand gradually in the future. And this system can be exported for developing countries by integration of these facilities. This is a microgrid for developing countries. This grid on that spot supply electricity, water, and the communication in developing countries and islands. And one more topic is interconnection of a country. This is called International Grid Connection Project in Asia. For example, Asian Pacific Power Grid and ASEAN Power Grid or State Grid proposed global energy interconnection. This is a future power grid. But now, gradually, we are constructing from Mongol, China, Korea, and next time to Japan. This is the last slide of my presentation. The objective of power supply is stable, reliable, clean energy with reasonable price. It's relatively easy to supply stable energy is by generation mix. Cost reduction is by efficient operation. And environmental preservation can be done by using clean energy technology. And by smart grid, energy saving, peak cut, load leveling, and efficient use of facilities and sustainable energy can be done by smart grid proposed by Obama, now undergoing. But the most important now in Asia is resiliency. Always Japan and the Asian countries suffered from tsunami and earthquake and so on. Then the resiliency, the first priority. Then resiliency and also cost reduction. It is not reliable by smart grid. It's an expandable network. What is expandable network? It's, I mentioned, expandable microgrid and smart community and supergrid. This is a future power supply system. Thank you very much for your attention.
Thank you. Thank you very much, Professor Ryuichi Yokoyama. Impressive speech about the resilient and sustainable future grid. So time is a little bit long, so
sorry.
I'd like to receive one question from the audience. So
yes,
is there
I'm Samsul Kamal from Indonesia.
Anyone, do you have questions for Professor
Yes.
Ryuichi Yokoyama? Please click raise hand in the
Please.
Yeah, I'm Samsul Kamal from Indonesia.
Okay.
Okay, professors. Thank you very much for time for the question, Professor. It's very interesting and indeed very smart idea for the microgrid. And my question is, if for kids in Indonesia, as you know, that Indonesia is, let's say, large scale in terms of area, consists of many islands. That is 17,000 islands. And then, it's piloted by sea. And then the load for the electricity is a very large gap between one island and another island. So my question is it still possible to construct the microgrid like that in terms of technical and economy? That's my question. Thank you very much, Professor.
Okay. This microgrid is very suitable for islands. As you know, Japan has also 10,000 islands, especially Okinawa area, and probably more than 30 microgrids in the Okinawa Islands. And Indonesia probably has more than 10,000 islands?
17,000.
17,000.
Yeah.
And probably you have 100 island project, Indonesia.
Mm-hmm.
I once
I heard that.
visited Bandung University. Some professor mentioned about they selected 100 islands and they are going to construct microgrid. But you mentioned, depends on the island, the profile of road is quite different. And the capacity, amount of road is very different. Then this kind of expandable microgrid is very good. You need not construct at one time. One time you select one village and to meet the demand and construct small one. And for next village, you construct a second one and connect each other. Then this microgrid is scalable. Not size is fixed. Scalable. Scalable means relatively cheap. Construction at one time is very expensive, but you extend one by one. Then conventional microgrid was said very expensive, but the expandable microgrid is not so expensive. Recently, PV panel is cheap, and the communication is also cheap. Only the battery. Battery is relatively expensive. Then we have to reduce the capacity of battery. That is the main point of design of microgrid. Thank you very much.
Okay, thank you very much, Professor.
Thank you very much, Professor Yokoyama and Samsul Kamal, Mr. Samsul.
Yeah.
So we would like to proceed to third presentation. Our third guest here is Professor Ryuji Matsuhashi from the University of Tokyo, Japan. And his topic is contribution of reserve capabilities and hydrogen-related technologies for realizing decarbonized power systems. Dr. Ryuji Matsuhashi received the degree of Bachelor from the Department of Electronics, Faculty of Engineering, the University of Tokyo, and the Doctor of Engineering from the same department. He became an associate professor at the Department of Geosystem Engineering, Faculty of Engineering, the University of Tokyo since 1994. He has become an associate professor at the Institute of Environmental Studies, a graduate school of frontier sciences, the University of Tokyo since 1999. Next, he has become a professor at the same institute since 2003. Then he has become a professor at the Electrical Engineering and Information Systems Graduate School of Engineering in the same university since 2011. Now, so Professor Matsuhashi, please give a presentation.
Thank you, Mr. Chairman. It is a great honor for me to make a presentation in this conference. So let me share the screen by my PowerPoint slides. Now you can see my PowerPoint slide. 見えますか？
はい、OK です。大丈夫です。今、
Thank you.
プレゼンテーションモードじゃなくて、編集モードになってます。
はい。Is this okay for you to see?
That's good. Yes.
Thank you very much. Thank you very much, Chairman. And as already we heard that very wonderful presentation by Professor Chan and also Professor Yokoyama. They were very kind to have made a very comprehensive presentation on microgrid or smart grid or future power systems. So here, I would like to talk about a rather simple story titled, my presentation title is Contribution of Reserve Capabilities and Hydrogen-Related Technologies for Realizing Decarbonized Power Systems. So here I would like to introduce to you one or two very simple stories and as a case study the power systems to realize decarbonized or energy systems. As all of us knows that COVID-19 is one of the most serious short-term global issues. Due to this COVID-19, we are forced to hold this conference also online, and we couldn't meet each other physically. So we feel that this is surely one of the most serious global issues. We must tackle this issue by global cooperation. And at the same time, concerning climate change issues, many philosophers and researchers argue that this is also one of the most long-term global issues. So everyone feel that COVID-19 is nowadays the most serious global issues. But in the long run, of course, climate change issues is also one of the most serious global issues. So we must tackle also this issue in the long run by global cooperation. So, and most of us also recognize that we need to decarbonize our energy system and our power systems in the very long run, and at least at the latter half of this century, many countries declare that we will realize, decarbonize our society. So, according to this tendency, of course, share of renewable energy in global electricity production. This is a figure. So, according to the director of United States National Renewable Energy Laboratory, NREL, and she explained to us the share of renewable energy in global electricity production, and already renewable energy provide more than 1/4 of total electricity production. Of course, major part of this is from hydropower, but also in the present times, wind power, biomass power, and solar PV is also increasing very rapidly. So we all see this rapid growth of renewable energy all over the world. Sorry, and this rapid growth of renewable energy, renewable power sources are causing some serious issues concerning stability of power systems. One of the most serious concern on stability of power systems is in this figure. This is in the southern region of Japan, Kyushu region, and already this is 2 years ago. The load and power supply in one day in May, 2 years ago. And this yellow part is from photovoltaics. Already, even 2 years ago, already this is a quite large amount of photovoltaic electricity comes from PV. And this black part is mainly fossil-fired power sources. And this green part is baseload power sources, mainly from nuclear and hydropower. So I want to say in this figure, one serious issue is how to predict PV output correctly, because forecast error of PV output is causing serious issues to power system operators. So here you can see that more than 6 gigawatt of output in one day is from photovoltaic output, but forecast error amounts, so in one day, 1 gigawatt or 2 gigawatt, or even more than 2 gigawatt. Of course, operators of power systems in large electric utilities pay many costs to predict more correctly how to forecast using machine learning and any kind of methodology. But still, this forecast error is sometimes happening. And in such cases, of course, we need some reserve capability, especially using fossil-fired power sources here. So we need anyway, not the base load, but these fossil-fired power sources to adjust to forecast errors. So for this reason, in Kyushu area, they use pump-up hydro to create demand in the daytime, and also they use interconnection among neighboring grids, and they sell electricity more 2 gigawatt to neighboring large electric utilities, and then they increase gap here to force many partial load operation of fossil-fired power stations, so that if this PV output shrinks, this many partial load operation fossil-fired power stations increase their output, and if this PV output increase more than here, at that time, this fossil-fired power outputs shrinks to more partial load. So from this methodology, now they are forced to adjust to forecast error of this kind of variable renewable power sources. But even now, they are increasing, and in order to realize perfectly decarbonized power systems, of course, photovoltaics and wind power generation must increase more than that. So in this case, gaps here decreasing and decreasing, and this means that they cannot supply reserve capability from fossil-fired power sources. So we need some innovative technologies to provide reserve capabilities. So also many of you knows that this kind of renewable energy, as I told you, that the share of renewable energy is increasing so much, not only in Japan, but also Germany, Spain, United Kingdom, France, Italy, United States, and Canada. Of course, hydropower is very stable power sources, but other renewable power sources, especially wind power generation and solar power generation, is variable renewable power sources. So their outputs are very uncertain and difficult to forecast. So we must deal with these uncertainties. And of course, also in China, wind power and solar power is world number one. So of course, also in China, they must deal with these uncertainties. So also, most of you knows that nowadays ancillary services are traded in many countries. This is the example in the United States, and then many of these reserve capabilities are traded in the market. Also, in now, frequency control, as Professor Yokoyama pointed out, is now this kind of technology is traded in the market in the United States, and also imbalance in electricity, spinning reserve, and operation reserve. All these are some relating reserve capabilities in power systems, and all these resources are traded in the market in United States. And also in Japan, we are now opening the market for trading such kind of reserve capabilities, of course, from a very fast adjusting technology like governor-free control, and also frequency control, and spinning reserve, operation reserve, traded in market in very near in the future, also in Japan. So this means, as I told you, even in now and also in future, we need so much reserve capabilities, not only by operating fossil-fired power stations, but also by some innovative technologies and end-use technologies like batteries or electric vehicles or some kind of hydrogen technologies or other energy storage technologies. So, of course, this is, I'm sorry for experts of power systems. This is a schematic diagram of power systems from very fast demand supply matching to very, very long term demand supply matching. Of course, in power systems, we must maintain demand supply matching from very short time period to very long time period. And now this is problematic here, especially as I told you, so prediction errors or forecast errors in photovoltaic outputs or solar power, wind power generations are happening, and this causes serious concern in power system operation. So, of course, we need battery or some other innovative technologies, and otherwise, we must curtail PV output or wind power output, and that leads to discouragement of renewable power sources, that leads to failure of realization of decarbonizing power systems. So, of course, as I told you, forecast errors happening so all the time. So we need to improve forecast technologies, and all over the world, they are competing how to forecast PV output like here, or wind power output like here, more correctly. Now, they are very important forecast. So technologies. Many researchers are tackling this problem by using so machine learning or some other technologies like remote sensing of clouds and weather condition and so on. And we are also doing such kind of researches in this research. But nevertheless, of course, we must keep in mind that even in this kind of forecast technologies will be progressed, we still take account of some forecast errors even in future. And this figure shows that this forecast errors fits more to Laplacian distribution than to normal distribution. That means very big forecast errors tend to happen more often than a normal distribution. So we must keep this fact in mind. So anyway, we have to take account of this kind of forecast error. So we need some technologies to absorb this kind of forecast technologies. And also nowadays, local power retailers are increasing, especially in Germany. They are called Stadtwerke, and they have approximately 1,500 Stadtwerkes in Germany, but also in Japan, local power retailers owned by municipal government are increasing as several tens of local power retailers are appearing owned by municipal government. And they need to deal with this kind of forecast errors because many of such local power retailers, they are targeting to provide electricity by their own producing renewable power sources. So they are procuring photovoltaics and wind power generation, biomass power generation, and other renewable power sources. So they must deal with forecast errors. And in this research, we are planning to absorb this kind of forecast errors by using electrolyzer. So using hydrogen cells and electricity and hydrogen co-production. So we try to deal with this kind of forecast errors. I mean, in the next figure, this is a very simple schematic diagram of local power retailers. This is a solar power generation, and this is a planned value, but actual value here, and imbalance appeared here, and this leads to penalty. And in this case, they are suffering from shortage of solar power generation. And of course, sometimes they suffer from surplus of photovoltaic output than planned value. This also leads to imbalance, and they must pay penalty. So in this case, we plan to electricity output here, this red line, and if the PV output is here, this surplus goes to electrolysis to produce hydrogen, and this hydrogen is to be sold to hydrogen station. And of course, if electricity shortage happens, this is nothing goes to electrolysis, but so PV output is more than the expected value. This large part goes to electrolysis, and this goes to hydrogen, is to be sold to hydrogen station. So anyway, planned value of electricity is very certain, and so they don't need to pay penalty here. And anyway, so uncertain part goes to hydrogen, and this is to be sold to hydrogen station. This kind of electricity hydrogen co-production, we could handle uncertainty, and net present value of this project was more than that only electricity retailers. This is co-production scheme. And also, of course, we could use batteries. In this case, so here is planned value, blue line. And if surplus or shortage happens, of course, so batteries discharge. And if surplus happens, batteries absorb this surplus quantity to store in the batteries. And then by this charge and discharge, they could compensate imbalances. So we need to compare the economy of using batteries and or using electrolysis to produce hydrogen, and we compare the economy of these two systems. And of course, it depends on the cost of electrolyzers and batteries, but hydrogen is quite good so economy in comparison with batteries. This is our result. And next, we need to move to the latter half of my presentation, more, how to say, macroscopic, large-scale explanation of decarbonizing power systems. As most of you knows that we must care about transient stability. This is also pointed out by Professor Chan as renewable power sources increasing, that inertia constant is decreasing. So this is causing the issue on transient stability. So we omit this basic figure. And of course, most of you also knows that the swing equation expressing acceleration of deceleration of synchronous generators as in this equation. And we are worrying about especially transient stability when some accidents like ground fault occurs in large-scale power systems. So if some ground fault occurs, transmitted electricity becomes to zero, but of course, so mechanical output of a synchronous generator continues. So balance in swing equation is violated, and the phase now beginning to increase. And here, of course, so operators of power systems use circuit breakers to shut down the ground fault transmission line. And then, of course, so one major transmission line survives.
Sorry,
and
the
in this
voice
time,
is gone.
yes? Could you hear? So in this red part, synchronous generator accelerates, and in this blue part, synchronous generator begin to decelerate. And if all this energy is decreased by this decelerating part, they can recover to here. But now the problem is increasing.
Sorry, Professor, the voice, your voice is not come up.
Oh, really? Can you hear now? Can you hear now?
Yes, we can hear you.
Okay, I'm sorry. I'm sorry. Now we speak slowly. Here we have renewable power sources. So we are worrying about, this is synchronous generators. This is assumption infinite bus. So if some ground fault occurs, in this case, we must shut down here by circuit breaker. But even in the ground fault occurs, this active power flow continues from photovoltaics to main transmission line. And also in this power grid, if the share of photovoltaic increases, the inertia constant decreases in these power systems. So phase shift are quicker than the power system only with this synchronous generator. And also, this active power flow continues even that the fault occurs. In such case, transient stability is very concerned. So we need to keep the share of this synchronous generator. So as a solution here, I propose here some of active power flow from this photovoltaics goes to electrolyzer to produce hydrogen, and this hydrogen goes to here to produce electricity by using synchronous generators. I mean that I use hydrogen turbine or combined cycle, not to use fuel cell, but to use a synchronous generator from hydrogen to make active power flow or to increase the share of active power flow to by synchronous generators. As such, even if the share of primary energy is maybe 100% from renewable power sources, we still keep stable AC power systems by using hydrogen and hydrogen turbine and synchronous generators. And as such, we have developed a power system model, optimization model for southern Japan area, Kyushu area, and we developed a simple power system model using optimization. And then I incorporated hydrogen turbine to keep stable power systems, even in the share of renewable power sources increased so much. And this is a linear programming optimization model incorporating every kind of power stations in Kyushu, and also constraint of frequency control and also transient stability and so on. And the scale of issue is approximately like this. This is the result. I'm sorry. This is the result. This axis means CO2 emission constraint from the just after the Great East Japan earthquake to CO2 emission zero. So this zero means totally decarbonized power systems. So you can see here, from here to here, rather very, how to say, not so sharp increase of cost of power generation, that is yen per kilowatt hour. About 100 yen is $1. So you can imagine here that the electricity cost. So electricity cost escalation is not so much to 10%, I mean 90% reduction of CO2 in this power system. But 100% reduction, I mean perfectly decarbonized power system, cost escalation is so much. I will explain the reason. In this figure, this is these two figures show that the capacity of hydrogen storage. You could see from here just more than 20% of CO2 constraints. Hydrogen is beginning to be used. And from here to here, hydrogen storage capacities increased so much. And here it is about 20 million normal cubic meter in hydrogen storage capacities. But here it is still not so much. But here, from 10% to 0%, perfectly decarbonized power systems, this increases so much. This is just 20 million cubic meter, but this is about 2,000 million cubic meters. So from 10% to 0%, hydrogen storage capacity increase approximately 100 times. And this causes that a quite steep cost escalation in the decarbonized power systems. And I'll explain, and from these figures, you can understand why such kind of steep increase of hydrogen storage capacities occurs. This is 90% CO2 reduction. CO2 is 10% of reference case. You can see this is 1 year, 8,760 hours in 1 year. You can see very, how to say, up and down, many up and down, but very roughly speaking, you could see weekly changes. So approximately 52 weeks in 1 year. So weekly change happens in a 90% reduction of CO2 emissions. But this lower figure shows that 100%, I mean, perfectly decarbonized power systems. So here you could see the change of stored hydrogen in 1 year. This is not weekly change, but seasonal change. So here, maybe February or March, hydrogen stored hydrogen becomes almost zero. And from June to July and summertime and autumn time, it hits the maximum value. And then again, so begin to decrease. So this means that hydrogen storage so absorbs the seasonal change of solar power. So these perfectly decarbonized power systems, we need a huge capacity of hydrogen storage that is causing very steep increase of the electricity cost in perfectly decarbonized power systems. So in conclusion, we have to go to the decarbonized power systems to tackle global issues as climate change. So we explained from such kind of global energy issues to how to realize decarbonized power systems. Of course, these global issues we must tackle by global cooperation. So we still need some innovation to more economical hydrogen storage technologies and other kind of innovative technologies to realize economical decarbonized power systems. That is my presentation. Thank you very much.
Thank you. Thank you very much, Professor Ryuji Matsuhashi.
Yes.
Very impressive speech about the decarbonized power systems. Does anyone have questions for Professor Ryuji Matsuhashi? Please click raise hand in your Zoom control panel if you do.
This is Yokoyama. May I have a
Okay.
question?
Yes.
Okay. Professor, thank you very much for your very informative and interesting presentation. And you mentioned as a storage technology, the
Yes.
first one, the battery and the electric vehicles and hydrogen.
Mhm.
However, these equipments are relatively expensive.
Mhm.
Some electric company have a plan to use pumped storage hydro, pump
Yes.
that generation. This is very conventional technology, not
Yes.
relatively cheap and large scale. How about in the future, the comparison of fixed cost and operation cost of hydrogen and pumped up?
Yes, Professor Yokoyama, thank you very much. This is, I think that a very important question. So I want to share a screen again to show some slide, complementary slide. And here, could you see this?
Yes.
And again, I compared some technology, especially in between batteries and hydrogen. Here, oh, sorry.
This one?
Yes. Or this one.
This one.
This is stationary batteries. You could see in the left bar, 50,000 yen per kilowatt hour. This price is developed by Tesla, Tesla company, and Powerwall of Tesla, which was certified quite recently, even also in Japan. And this is a price of hydrogen. And oh, I'm sorry. This is a price of hydrogen sold to hydrogen station. We also made hearing to Air Liquide Japan and also Iwatani industry to deal with this hydrogen. And nowadays, they are perhaps they are purchasing hydrogen by this price. In this case, I think that the cash flow is better in hydrogen than in stationary batteries. But of course, we expect some technology breakthrough also on stationary battery, more economical than the present value. So these kind of technologies we could expect more and more in future. And of course, as Professor Yokoyama pointed out, pumped storage is also very promising technologies and perhaps economical than the battery and electrolyzers producing hydrogen. But so in Japan, the land is limited. Also, environmental constraint is also very severe. So I suppose that due to this limitation, we cannot expect so much in the future. Pump storage power station will increase further. So from now on, we expect rather such kind of innovative technology such as battery, hydrogen, and electric vehicles. These, for the moment, I think like this. But anyway, I appreciate Professor Yokoyama's comment. Thank you very much.
Thank you very much. And also disadvantage of hydro pump that is it takes more than 10 or 20 years to construct.
Yes, yes. So this is also very long run.
Long run.
So yes.
Okay. Yes, thank you
I
very
agree.
much.
Yeah. Thank you very much.
Thank you very much. So, okay. I would like to close morning session.
Excuse me, Professor.
Mhm.
Excuse me. There is another question from.
Oh, okay.
Yes.
From, okay.
Can I ask a question too?
Mhm.
Thank you for the good, let's say, informative presentation, Professor Matsuhashi.
Yes.
I am Badasrest from Western Michigan University, Michigan. I have a small question. You mentioned that using hydrogen, using extra, let's say, energy produced by PV to produce hydrogen. But you also said that where you also use hydrogen to generate the electricity using micro turbines, not the fuel cells, not the fuel cells. Why you don't want to use the fuel cells?
I see. Thank you for the very important question. And this one is that small power retailers. In such case, of course, we also think of using fuel cells. Fuel cell is also very nice, innovative technologies, and also that by collective use or remote control of many fuel cells, we could respond to forecast uncertainties or compensate imbalances of power systems. So fuel cell is also very, very nice, important technologies in future. But as I mentioned, here, this is a very macroscopic strategy to, in order to realize decarbonized power systems. So in the very huge power systems, if we must realize decarbonized power systems, we need to keep some inertia constant. That means we must keep the share of active power flow from synchronous generators. But photovoltaics, wind power, and fuel cells, they don't have inertia. We want to increase the share of synchronous generators even in the decarbonized power systems. So from this point of view, we would rather use hydrogen turbine not to use fuel cell, but to use hydrogen turbine and synchronous generators to produce active power flow with some inertia. This is what I meant. But of course, in the microscopic point of view, of course, also in future, we would use fuel cells also in maybe microgrid, some smart grid, or local energy systems, especially zero energy house or such kind of innovative technology, they normally use photovoltaics and also fuel cells. So this is my response. Thank you very much. 野茂先生、今の聞こえてましたでしょうか？
はい、私のは大丈夫でしたけども。
はい。
はい。はい。Okay?
I appreciate the comment. Thank you very much.
So, again,
Yeah,
I'd like to.
Yeah, thank you.
Okay.
So again, I'd like to close morning session. So maybe please, Mr. Samsuru, would you please mute your mic?
Yeah. Yes.
Okay.
So,
I'd like to close morning session. Thank you very much for all speakers, contributors, and all participants. So we make a break time until 1:30 p.m. Okay. Thank you.
thank you very much.
Thank you very much.
Thank you.
Thank you.
May I have your attention, please? Thanks to the 3 keynote speeches for their wonderful speeches. Now we'll end the morning session, and in the afternoon, there are the 4th keynote speech and 4 sessions into different conference rooms. So we kindly remind you, please check your room ID according to the conference program and log in the room 10 minutes before your session starts. Let's come back and 1:30 p.m. for the 4th keynote speech. Thank you all. See you later.
Thank you.
you.